Don't do like that next time.
Ló bá rẹ́rìn-ín sẹ́sí mo rẹ̀ báyìí gbogbo orí mi dìde ni mo fẹ́ lè ṣubú.
Ṣé ọmọ orúkọ yín ni? Báwo ló ṣe mọ?
Ọmọ mi náà ìyàwó náà lọ.
Good afternoon, class.
Good afternoon, ma.
Eniola, are you here? Eniola, is Eniola here? Who is the course rep? Who is the course rep? Eniola is not here. Who is the course rep of education here? Is education course rep around here? Chemical engineering. No course rep is available here.
I am available, ma.
What's the name?
Miriam.
Miriam. Others should mute themselves except Miriam. Every other person should mute except Miriam. Miriam, what's your name on this?
Ma?
Okay, Miriam. I'm going to make you a co-host. So you're going to help me organize the class. Make sure everybody is muted.
Okay, ma.
And help me take attendance. Thank you. Please, as soon as you're entering the class, make sure you're well muted. Because I don't want distraction, please. We don't have luxurious time, so we have to optimize our time. So good afternoon, class. So today, you had a class with Dr. Abayomi. I supposed to be available last Thursday, but I was not notified on time that he was done with his class. So in today's class, we'll be looking at benzene and aromaticity.
Voila.
Benzene is not voila, okay? So I think before I go further, I want to talk to every one of you. Section 213 is a very simple course, but Johnny said that it's very voluminous. The only good things you can do for yourself is to be available for the classes. In my own class, I'll be giving you classwork, which you are going to be doing submitting on Google Classroom. The essence of the classwork is for you to familiarize yourself with chemistry and how chemistry question, especially in this course, is being asked. I also have a YouTube channel where I made an audio recording of most of the topic, at least about 95% of the topics are on my YouTube channel. So after each class, you can also go back and watch the video because the class is recorded on YouTube. You can also go and listen to the audio lecture, which I uploaded on my channel, Ask Dr. Anita Kim. So it's going to help you. And there's some questions too that will assist you. And I also have a platform where I do mentoring on my WhatsApp. So if you're interested, you private chat me. Course Rep is going to add me to your platform for people that are interested for mentoring. So you can join the platform. The essence is that the last sets, some of them had a very good grade. Some people had up to 98, 90 something in this 2 and 3. So it's something, is a doable thing. So I don't know the fear and what you've heard about 2 and 3 that made you to be scared of the course. The course is something you can always get very good grades. But the truth is that you must read. You must read in between the lines. You must be available for the classes for you to understand the basis. If you do that, you always smile at the end of the course. So I'm wishing you success in this particular journey. Thank you very much. So today's class, we're going to talk about benzene. And whenever I am moving on a very high speed, just raise up your hand. So I will pause. I'll listen to what you want to say. If I'm too fast, I will reduce my pace. If I'm too slow, I will increase my pace. But the essence is I want you to understand the course. Okay? All right. Thank you. So benzene and aromaticity. So when we talk about benzene, we're talking about a cyclic compound that is conjugated. So when you talk about aromatic compound, it's compound that behave like benzene. So that's what we'll talk about, benzene first and aromaticity. So we're going to be moving. In today's class, we're going to look at in the introduction, we're going to talk about what are aromaticity, how do we name benzene, what are the sources of benzene, what are the reactions that this compound can undergo, and what are the substituent group effects in benzene, and what are the addition reactions of benzene. Now, the essence of this slide is for you to understand what you're expected to know. So you're expected to understand what benzenes are and what are the characters of aromaticity, what makes a compound to be aromatic. You're going to also know how to name benzene as a compound. You're going to also know what are the sources you can obtain benzene, the reactions and effect of substituents. So this topic is very interesting. Just let's write together. So benzene, like I said, is the simplest member of a cyclic compound known as aromatic hydrocarbon. Oh, I don't want noise, please. So when you talk about benzene, you talk about the simplest form. That's why we say any compound that is aromatic behaves like benzene, because benzene is the simplest member of the group of cyclic compounds known as aromatic hydrocarbons. The word aromatic is derived from aroma, means pleasant smell. But not all aromatic compounds have pleasant smell. So not every aromatic compound has a very sweet smell. Some of them are awful. Now, benzene, the molecular formula for benzene is C6H6. Now, this benzene, I'm not going to read slide because slide is for you. I'm going to explain slide. This benzene have the same number of carbon like any other hydrocarbon, but they differ in the ring and the conjugation. Now, remember, in aliphatic hydrocarbons, which are alkane, alkene, alkynes, alkene and alkynes are unsaturated. Benzene is also unsaturated because of double bond. What makes a compound unsaturated is presence of double bond. So the more the double bond, the higher the unsaturation. You may do yourself good by muting. No, it's not good. Please make sure you mute. Miriam, please mute everyone.
Yes, ma'am.
Now I want to please. Okay, thank you very much. It's very wise that you yourself you mute yourself before you enter online class. Okay, don't allow somebody to mute you. Okay, thank you. Now, like other unsaturated hydrocarbons, which are alkane and alkyne, benzene is an unsaturated compound. But there's something about benzene. Benzene does not behave like other unsaturated compounds because benzene wants to protect its own aromatic nature. Now, every other unsaturated compound they are going to look at, I don't think they've been taught about hydrocarbons. There's something about them. They undergo addition reaction. Now, I want you to ask yourself, why are they undergoing addition reaction? Because that presence of unsaturation means they are empty. They are still space. Let's liken unsaturation as when you are testing. Now, if you're testing because you are coming from a far distance with sun, it's different for somebody that is in the house that is feeling testing. Now, you that is coming from under the sun, you can even finish 2 bottles of water before you calm down, before you become saturated. But the person staying in the house will just take a sip and the person is okay. Now, depending on level of unsaturation. In the same manner, the more the double bond, the higher the unsaturation and the higher the level of addition reaction. Addition means you're adding because there is vacancy for you to fill in. So that is why we talk about addition reaction. Benzene, when benzene undergoes addition reaction, there is always problem. It ceases to be benzene, it becomes cyclic compound. It becomes cyclic compound.
And I will chill. These people will come now. I know they don't sleep immediately.
Oluwa, Pelumi, Sarah, Abigail, Azizat, how can you enter a class and you expect somebody to mute you? When you enter a class, you mute yourself. Sarah, mute yourself. Don't disturb the class. Who is this Abigail? Did she just log on and she's busy doing something else? I'm going to know people that are in the class and people that are not in the class. I know my method of knowing. So please, when you enter my class, mute yourself.
Hey, thank God. Benzene.
Like I said, benzene is unsaturated aromatic compound that does not undergo the typical reaction of unsaturation. I've said it several times and I'm going to say it again. The reason is that benzene must maintain its aromatic nature. To make sure that the aromatic nature is maintained, benzene does not undergo addition reaction. So what does benzene do? Besides, benzene does not undergo oxidation reaction. So benzene, because of its unique nature, but benzene does not decolorize potassium permanganate. Remember, in your 223, we talked about how to identify unsaturated compound using potassium permanganate. And we said that potassium permanganate is going to be decolorized if a compound is unsaturated. Because benzene does not undergo typical reactions of unsaturation, benzene will not decolorize potassium permanganate. Benzene does not react with halogen except in the presence of a catalyst, because the essence of the catalyst is to speed up the reaction without interfering with the unique nature of benzene ring. Now, like already said, the benzene does not undergo addition reaction. Rather, it undergoes substitution reaction. In substitution reaction, remember benzene is C6H6. The hydrogens are being substituted with the electrophile. So the typical reactions of benzene is electrophilic aromatic substitution reaction. I repeat again, the typical reaction of benzene is electrophilic aromatic substitution reaction. Now, every word in this statement I made is very important.
Let me drop mine.
Miriam.
Mom, using them already.
Electrophilic.
Ma, what did you call the
It must be electrophilic aromatic because we are dealing with benzene, and it must be substitution reaction. So electrophilic aromatic substitution reaction is a typical reaction of benzene and aromatic compounds. So benzene does not have any isomer. All the carbon atoms are everywhere. So all the carbon atoms are very equivalent. So because it has a very unique type of unsaturation, different from alkanes or alkynes, benzene does not undergo addition reaction. Now, August Kekulé proposed a cyclic structure of benzene. And he talked about that benzene is a hybrid of two structures called canonical structures. That is why benzene is always being represented as a ring with circle, meaning that these bonds are alternating. They are not static, they are mobile. We call them mobile electrons. So they're always moving. That's why they can take any position as much as the conjugation is maintained. So benzene is conjugated cyclic compound, which is, according to August Kekulé, hybrid of two canonical structures. So whenever you want to write anything that draw any structure of benzene, either you put circle at the middle or you put bond, and that bond must be conjugated. So you can use any of the bonds whenever you're writing equation or reaction, but just know that these bonds are alternating. When we're going to talk about mechanisms that involve benzene, you will understand how these bonds alternate. So let's continue if there's no question at this stage. Now, the reason why benzene does not undergo addition reaction is that these bonds are not real, meaning that their position is not real. So when you, like a previous slide where we're talking about the bonds, you can see that that's a hybrid, that is always the bond was moving, and that hybrid structure is represented as a ring, meaning that you cannot say that this is a position of this bond. The bonds are always moving. Because there is no existence of real double bond in benzene, that is why it fails to undergo the usual addition reaction expected of unsaturated hydrocarbons. Because these bonds are always alternating. There's no reposition. When you talk about that, this bond is in position 1. In the next, before you know it, they've moved to position number 2. So you cannot pinpoint the reality of the bond, where they belong. So that is why. And these bonds, they are always, the single bond is always alternating double bond. That is also what makes us to have only existence of 1,2-disubstituted isomer of benzene, where we're going to look at the isomers. Then the carbon-carbon bond length in benzene, according to Huckel, is equal. And between that, a pure single and a double bond. This resonant hybrid structure is more stable than their unit contributing structures. Meaning that if you're talking about stability, the bond that has a ring is more stable than those two bonds added together. So if I want to really talk about stability of my benzene, I will use ring at the center. But as long as exam and test is concerned, you can use any of the structure, as much as single bond is alternating double bond, indicating conjugation. If you draw benzene without indicating conjugation, it ceases to be benzene. So when you're talking about canonical structure, you're talking about the two structures that are made up of benzene ring. That is what we call canonical structure. So the two canonical structure is one made a hybrid structure of benzene. Like I've said initially, that because of the stability of benzene is very stable, and these bonds are not real. That is why benzene prefers to undergo substitution reaction instead of addition reaction, which is typical of any other unsaturated compound. Benzene also resists any reaction that can destroy its aromatic nature. Like I said, that is why benzene cannot undergo addition reaction, because if it does, it will become a cyclic compound. And benzene is not just cyclic, it's cyclic aromatic. So that aromatic nature is because of the conjugated bond in cyclic compound. So if there is no conjugation, it is not benzene. So in order for this benzene to protect this aromatic nature, it cannot undergo addition reaction. So what are the characters that are peculiar to benzene that confirm its aromatic nature? What are the signs that we can say, this is benzene because it has the following aromatic behavior? Number 1, benzene does not undergo oxidation reaction. Means benzene cannot react with permanganate or any oxidizing agent because of its aromatic nature. So benzene is resistant to oxidation reaction. Benzene is resistant to addition reaction, and it can easily undergo substitution reaction. Benzene is unusually stable, which is evident by its heat of hydrogenation and combustion. So the stability is a character of aromatic nature of benzene. So what are the 3 aromatic character of benzene? Resistant to oxidation, resistant to addition reaction, unusual stability. 3. Resistant to oxidation, resistant to addition reaction, and unusual stability. Those are 3 peculiar characters that make benzene to be aromatic. So now we're going to look at the modern molecular orbital picture of benzene. Number 1, the carbon and hydrogen atom are planar. The carbon and hydrogen atom of benzene are planar. When something is planar, it means that I can see the end from where I am because all the carbon are lying on the same plane. So when viewed, benzene is planar. Secondly, because of the double bond, the hybridization in benzene is sp2. So benzene is sp2 hybridized. First one, the carbon are planar. So whenever we're talking about aromatic nature, we are going to also see all this. Now, in sp2 hybridized, remember we talk about when you're going to be taught the hydrocarbons, you're going to understand that sp2, which is alkane, has bond angle that is approximately 120 degrees. Now, whenever we are talking about bonding, there's difference between carbon-carbon bond and carbon-hydrogen bond. And now, if you're talking about hybridization of carbon is different from hybridization of bond. Listen very well. If I'm talking about benzene, I want everybody to use pencil or biro to draw the benzene ring on your notes. Draw benzene ring on your notes. I want to explain something to you. Now, having drawn that benzene ring, now there are bonds between carbon and carbon. And there's another bond between carbon and hydrogen. Is that clear?
Yes, ma'am. Yes, ma'am.
Now, between that carbon-carbon, that bond that connects the two carbon is what we call carbon bonding. And that carbon bonding is what we call sp2-sp2. But that bond between carbon and hydrogen is what we're calling sp2s. That S is for hydrogen, sp2 is for carbon. So now, if the question is that the bond between, if the arrow is on the bond between the two carbon, the answer is sp2, sp2. But if the arrow is on carbon itself, the answer is sp2. Listen, there is difference between hybridization of carbon and hybridization of bond. Hybridization of bond, it means that the two atoms that are being connected by that bond you sum the two. That's the hybridization of the bond. The hybridization of the carbon is the nature of that carbon in the compound. If you look at all the carbon in benzene, all the carbons are sp2. But if you're talking about bonding between two carbons, it becomes sp2, sp2. But if the bond you're looking for is bond that connects carbon and hydrogen, because the carbon is sp2, hydrogen is s, it becomes sp2s. But if I'm looking for carbon on hydrogen alone, it becomes s. Do we understand that? This is very important because you cannot, and whenever you're talking about 213 exam, you cannot miss issue of hybridization. And I think in my YouTube, I think I talked about hybridization because I dealt on alkane and alkane before talking about this. So you can also go and watch and understand more. Please explain again. What I want to say is that whenever you're asked about hybridization for saturated hydrocarbon like alkane is sp3. Unsaturated, that is alkane, is sp2. That's double bond. The triple bond is sp. This is hybridization of carbon in these compounds. Then if it's hybridization of bond, you look at the two atoms, either carbon, 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 hydrogen, carbon, nitrogen, or whatever. The atoms that made up that bond, the sum of their individual hybridization is the hybridization of the bond. Now, in this particular slide, if I'm talking about the hybridization of bond between carbon and carbon, because I'm dealing with benzene, the answer is sp2, sp2, because all the carbon in benzene is sp2 hybridized. But if the arrow is on carbon connecting to hydrogen, that bond that connects carbon to hydrogen, you can see the bond that connects carbon to hydrogen. If the arrow is on the bond between the carbon and hydrogen, The answer is sp2s, because this bond is made up of carbon and hydrogen, and the hybridization of carbon is sp2, while that of hydrogen is s. So the sum is the hybridization of the bond. So when I'm talking about the atoms, I'm talking about individual atoms. If I'm talking about the bond, I'm talking about the two atoms that made up the bond. I think that should be okay. Now we are talking about benzene. Now, each of the sp2 hybridized carbon, there is one unhybridized p orbital lying perpendicular to the plane and 3 hybrid orbitals. Now, why? That is why we have sp2, meaning 1 s and 2 p, making 3 hybrid orbitals. Now, I think if it's a physical class, I would have drawn a structure. Now, if you look at carbon is made up of 6 electrons. In that 6 electrons, we have 1 s2. Listen very well so you can follow me. 2 s2 and 2 p2. What is hybridization? Hybridization is a mixing of 2 or more atomic orbitals. These atomic orbitals is s and p in this case, on the same energy level, of the same energy level. Now, because I have 1s and 2s, meaning that 1s cannot participate. So I'm going to cancel 1s. I'm going to deal with 2s and 2p, because 2s and 2p are on the same energy level, to form a new hybrid orbital. The new hybrid orbital will be sp2. Now, in alkane, this needs to be demonstrated. In alkane, but when you be talking about hydrocarbons, you're going to understand this very well. I want you to just have an overview of what I'm saying. Now, in hybridization, 1s cannot participate because they are not of the same energy level. So we're going to deal with 2x and 2p. If I were you, I'll be writing it on my paper. So 2x2 and 2p2. This is carbon in their ground state. Now, an atomic orbital of s is how many? S has 1 atomic orbital, while p has 3 atomic orbitals. So under that s, draw 1 box. Under p, draw 3 boxes. Are you there?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Under x, draw 1 box. Under p, draw 3 boxes. Then under that x, remember we have 2s2. So write 2s2 on the top of that x. Under p, write 2p2. Done? If you've done, say yes. So that
Yes,
I can
ma'am.
follow. Okay, now because we have 2s2, 2 electron on s, so put electron, remember it's single before pairing, half up, half down. And then on p, put 1, 2, up. Do you understand what I'm saying? How to arrange, fill up an electron? We've done it on our FSC, right? So in my p, s orbital, I'm going to have half up and half down. The shell is going to be complete. Then in my p orbital, I'm going to have 1 up and 1 up, 2 orbital. Then 1 orbital is going to be empty. Is that done?
Yes, sir.
Yes, ma'am.
This is
Yes, ma'am.
carbon.
Yes.
This is carbon in ground state. So you have to repeat that structure under. Don't put anything in the box. We're going to talk about excited states. In excited states, repeat that box of 1x for 1 box for x, 3 box for p. Then put on top of s, put s, on top of p, put p. Now, in ground state, these are what these atoms have originally, but they cannot react except they're excited. This is what, whenever you're excited, example is that when you are in the class and all of a sudden you have your phone an alert, you open your phone, SMS, credit alert, and the amount you're expecting lands. Number 1, you're going to smile, you're excited. And at that moment, if there is any of your friend that is beside you, you are willing to take that person out because maybe you're expecting 5,000 and maybe 20,000 enter. You're excited, you just want to exhibit excitement. So for any reaction to occur, these atoms must be in excited state. And now in that excited state, S orbital have seen that I have two, but P, one person is not having anything. Just like you have money, excess money, and your friend is saying, I'm hungry. So that is that friend in your group, and you have enough. It is easier to say, okay, take, since I have to take one. So that is what S did. S in excited state, S was able to give one to that P orbital that does not have any. Now, on that P orbitals, I want you to write S, X, Y, Z. On the P orbital, there are three. We have X, Y, Z on it. So on that excited state, I want you to put X, Y, Z. And on that Z, that's where X is going to borrow, S is going to borrow 1, 2. So all of them are going to have 1 electron on their orbital. Are you following me?
Yes, ma'am.
Yes, ma'am.
Okay. Now, in that case, how many electrons do we have in S orbital?
One.
P orbital?
1.
3.
3. So when you combine the S and P, how many? What are we going to have? We are going to have SP3, right?
Yes.
Yes,
Is that?
Yes,
Are
ma'am.
we having SP3?
yes.
Yes,
Yes,
ma'am.
yes.
That SP3
Yes, ma'am.
is the hybridization for saturated hydrocarbon called alkane.
This hybridization is kind of
Now, on those spaces, hello, on those spaces where we have 1 electron, go and fix hydrogen beside them. Pick on X orbital, fix hydrogen. On that P orbital, that when there are 1 electron, let the other electron be hydrogen, hydrogen, hydrogen. So I'm going to fix 1 hydrogen, making it 4 hydrogen, right? Now,
Yes, ma'am.
that is carbon bonding with 4 hydrogen. That is what we have in methane. Draw the structure of methane, carbon having 4 sites and having hydrogen there. That is sp3. Are you following the storyline?
Yes, ma'am. Yes, ma'am.
So this
Yes,
is
ma'am.
sp3. So that's why we have sp3. Now repeat that structure again. We want to do sp2. Repeat that structure where you have S and P in their excited state. When you repeat that structure, now that PZ is not going to participate in bonding. Now remember what we are in the slide say at each sp2 hybridized carbon, there is unhybridized p orbital. That unhybridized p orbital is the p orbital that is not participating in bonding. That is PZ. So you remove that PZ. That PZ is not going to participate in bonding. It's going to be used as a double bond. That is unhybridized. When you remove it, it means how many is remaining in p orbitals?
2, ma'am. 2, ma'am.
2. So at the end we have sp2. So that is what happened in double bond. Remember that because the one of that p is not is unhybridized, is used in forming double bond. That's why they say it's unhybridized, lying perpendicular to the plane. That is why we are having the double bond, and that we call it pi orbital. Now, in the same manner, if you repeat that structure again, we come to sp, where the other p orbital, which is py, is also going to be used, be all hybridized and used in forming double bond. That's why we have 2 pi orbital and 1 sigma bond in sp orbital. That's why alkyne, that is triple bond, is going to be sp p hybridized. So I think you'll be able to understand how we have sp3, sp2, and sp. So that unhybridized is what is being used in forming double bond. So in sp2, we are going to have one unhybridized, while in sp, we are going to have two unhybridized. But in sp3, we don't have any unhybridized because all the p orbitals are participating in bonding. Sorted. Can we continue?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Thank you.
We
So,
don't understand. If you can please
I
come
have a
again.
question.
okay, ask question.
Okay, ma. Ma, about that conjugation you were speaking about, I was raising up
Okay.
my hand. You
Okay, sorry.
were speaking about conjugation. Conjugation. What do you mean by conjugated system or conjugation? Like
Okay,
in the
thank you.
benzene compound.
Yes, in any system, when a system is conjugated, it means that single bond is alternating double bond.
Okay, ma.
Yeah, that's so any system that is we can have a diene that is conjugated, meaning that single bond alternate double bond. So wherever you see single alternating double bond, we say the system is conjugated.
Okay, ma.
Any other question? Please, anything you don't understand, let's talk about it now.
Please, can you
Don't be
explain this
shy.
hybridization again?
Okay, were you drawing what I said they should draw?
Yes, we were, and then we lost you.
No, I don't want to say we. I want to say I because I don't think you are in the class. You are in your
I'm
own.
in the class.
Or are
I
you
tried the
using the? Are you
conversation,
using?
I'm also saying
Are
that
you more than one there?
I'm just by myself.
Yes. So you cannot say we. So
If you check the comment section, there are also
so
people
what
there
award
saying
did you draw? So let me know where you are, so I know how to help you them.
okay, I was at the carbon in their ground state. I was drawing the 2s2 2b2 orbitals, and then I got confused.
Okay. So okay. Let me start again. I hope everybody is listening. Now, carbon in their ground states. Remember, for a compound to hybridize, number one, it must be one or two or more orbitals, and they must be on the same energy level.
I like this stuff.
Two or more atomic orbitals. Remember, atomic orbital is sp df. So two or more of them can hybridize. That's why it says it takes two to tango. So for a bond to be formed, two teams must be involved. That's why if marriage is about two. So everything is two, right? So for bond to form, we need two orbitals, minimum of two or more. Now, and these orbitals, they must be on the same energy level. The electronic configuration of carbon is 1s2, 2s2, 2p2 because it's 6 electrons, right? Atomic number of 6. Now, in that energy level, 1s is odd because it's not on the same energy level with 2. So that's why we cancel 1s in hybridization of carbon. So we are dealing with 2s and 2p. Now, in this 2s and 2p, I say you should draw structure of s orbital. S has 1 orbital, p has 3 orbitals. Draw under that 2s, put 1 orbital. Under the 2p, put 3 orbitals. Now, this is carbon in their ground state. And I say for carbon, for any atom to react, they must leave ground state and move to excited state. So for carbon to be excited, remember, after drawing those structure or those orbitals, in S, put the electrons single and pair. But in P, you're going to put just single 2 electrons. That is their ground state. So for them to react, they must be in excited state. Now, in excited state, I cannot be happy, and my friend that is beside me is, okay, let's use in the class. I cannot be happy. My friend is not writing anything, and I have 2 biro with me. Because even if it's not my friend, because in that state, I have SS. Okay, I have by after writing, give me. So in that excited state, S has 2 electrons, and one of P is not having anything. So out of excitement, the S is going to loan 1 electron to that empty P orbital, and all of them is going to be fine. Everybody is writing. Nobody is not writing in the class. So that is that they are reacting. So they can interact because everybody is happy. That's the excited state. So because I have 1 S and 3 P, that's what they call SP3. P is 3, S is 1. So 1 S is as good as saying S. So 3P is P3. So that's why we have SP3 orbital. SP3 hybridization. So this SP3 hybridization is typical of saturated hydrocarbon, which example is alkanes. Now I said when you go to those spaces, remember normally single pairing singly before pairing. So we've done all the singles, they need to pair because every orbital is made up of 2 electrons. So the remaining electron is going to come from hydrogen. That's why I said put hydrogen on each of the boxes of the orbitals. So we're going to have 4 hydrogen. If you've done that, you realize that, remember, we are dealing with carbon. Carbon is bonding with 4 hydrogens. That is what we have in methane. Methane is a typical example of alkane. So when you draw carbon and draw 4 bonding sites and put hydrogen, we call it CH4, which is methane. This is sp3, typical example of sp3. Then, furthermore, in alkene, which is sp2 hybridized, what happens is that the p orbital, under that p orbital, we have x, y, z. Is 3 orbitals. They are called degenerate orbitals. So then for S, that last z orbital is all hybridized according to the slide. They said at each sp2 hybridized carbon, there is an unhybridized p orbital lying perpendicular to the plane of the 3 hybrid orbitals. Because this pz is not going to participate in bonding, we call it unhybridized. So in that case, it's going to be used to form the double bond. And because that's what we call it a weak bond, and that's what we call pi bond. So because it's not participating in bonding, so we remove it, meaning that my p orbital is remaining px and py. So making it to be sp2. My p9 is 2 because 1 I've been used in forming double bond, making it sp2 hybridized, which is typical of all double bond, benzene and alkanes. Now, if you go further, you can also remove the py and use it to form another bond, making it 2 unhybridized orbitals. Both of them lying perpendicular to the plane of the remaining 2 hybrid orbitals. Now, the 2 hybrid orbital is S and P. So we have sp in alkyne because of triple bond. Because py and pz are used in forming double bond. So that is the story of hybridization. I hope you are clear now.
Yes, ma'am. Thank you.
All right. So we can continue. So these are actually what I've said so far. So this is also what I said. That is why these 2 p orbitals are lying overlapped literally with each other on each of the sides. That's why we are having whatever you're seeing there is the p orbitals lying perpendicular to each other. So wherever you see double bond, it means that p orbitals are lying perpendicular to themselves. Remember, it is 2 carbons. Now, listen. If you look at alkane, it takes only 1 carbon to form bonding. Example is methane. But from alkane and alkyne, it must be 2 carbons. That is why if you look at the diagram, you realize that we have 2 carbon, one bringing 1 p orbital, and another one bring another p orbital for them to form bonding. So that's why whenever you're writing the homologous series of alkene, it starts from ethane, E2. But for alkane, it starts from carbon number 1. But for alkene and alkyne, it starts from carbon number 2 because it takes 2 to form that double bond. Because it's becoming noisy. I can't cope.
If I describe simple of any of them, when I'm not Bilal, but then I was black.
The class is noisy.
Black one then.
Yeah, I think black
John.
people are not very common. Black Arabs are not really common.
See, I'll start taking some people out of this class. Anybody that disturb my class, I'll take them out. And they will not come to class again.
I hope you're making.
Ola Iwole. Okalonwo. Please, Ekene, you should mute yourselves. Anybody that disturb my class again, I'm going to automatically remove the person from this class. Don't disturb the class now. You're not the only one here. Okalonwo. Please, I don't want noise again. Please, 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 don't disturb my class. The weather is there is sun already, and chemistry needs calm environment. Please, let's make this class conducive for everyone. Like I said, in homologous series, when you're looking at the hydrocarbons, you realize that when you come to alkane, you start from carbon number 1. That is where we have methane. But when you come to ethane, alkene, and alkyne, you start from carbon number 2. Because for a bond to form, 2 carbon must come together. Each of them is going to release one electron. Then that's why it takes 2 to tango. Carbon A will release 1 electron, carbon B is going to release another electron for them to form bond. In forming a bond, we need 2 electrons. And remember, in our p orbital, we have only one electron. So we have 2 p orbitals to come, each releasing one p z orbital for them to form a bond. And that is what is being represented on this slide. Now remember that this electron, this double bond, oh God. What is this? Jomiloju. Hey, you guys are really, people should not make me to start having another mindset about you, please. I know we are civil, let's be civil. Now, these electrons, these unhybridized p orbitals, they form pi electrons. These pi electron clouds are very weak. That's why for a reaction to occur, this is a bond that breaks for a reaction to occur. This pi electron is just like friendship electron, friendship bond. Friendship bond is a very weak bond that anything can cause it to break. There's no problem. But when there is problem is when sigma bond breaks. That's what happens in divorce. But that's why I say broken courtship is better than broken marriage. Is because the bond in friendship or courtship is still pi bond, which is very weak bond. So whenever you talk about a reaction occurring, you know that it is the pi bond that breaks. So in the double bond, is the pi bond that is big bond. The main
example of bond was how strong they are.
Oludere and Feishara. Be careful, I'm hearing your voice and your interaction. Zainab. So why I'm giving this illustration for you to understand what I'm talking about. So pi bond is a weak bond that breaks whenever a reaction is occurring. But whenever a sigma bond, that's why if you want when you get to oxidation reaction, they tell you that tertiary alcohol cannot be oxidized. When you want to oxidize, it's going to cause cleavage of the bond. When a bond is clipped, it means that the compound is normal again. That is going to form another compound entirely. The compound are not together because sigma bond is being involved. So pi bond is a weak bond that breaks during chemical reaction. Whenever sigma bond breaks, the compound splits. Now, another thing you should know is what are the characteristics of aromaticity. For a compound to be aromatic, the compound must have the following character. Number one, the compound must be cyclic. It means aliphatic compounds are not aromatic compounds. Two, the compound must be flat or nearly flat. Talking about compound being planar. Three, the compound must have the localized pi electrons. The localized, that means it must be conjugated. When the electrons are delocalized, means they can move around. So the compound must have a cloud of delocalized pi electrons that are mobile. Remember, for a compound to be mobile, they must be conjugated. That's what made them. You're not sure of where A is. They can easily change their position. Then the compound must be able to obey the Huckel rule. Huckel rule of 4n plus 2 pi electrons. So we're going to use this Huckel rule to explain how a compound is aromatic. So characteristics of aromaticity: cyclic, planar, conjugated, or the localized pi electrons, and must obey Huckel rule of aromaticity. So that we know that these are the 4 characteristics of aromaticity. Remember, initially we talked about what are the character that made benzene to be considered aromatic. Now we're talking about general characteristics of aromaticity. This one goes beyond benzene. So if I see a compound that is not aliphatic, how can I, and the compound is not benzene, how will I know that this compound is aromatic? Number one, I must make sure that the compound is a cyclic compound. If the compound is a cyclic, it is not aromatic. I must make sure that the compound is planar. I must also make sure that the compound is conjugated, meaning it contains cloud of the localized pi electron. And most especially that it obeys the Huckel rule of aromaticity. Huckel rule say 4n plus 2 pi electron. That n means the number of ring. So we're going to use the Huckel rule to predict aromaticity of some compound in upcoming slides. Now, a compound being conjugated alone cannot validate aromaticity. Whatever that happens, Huckel rule must be obeyed for a compound to be termed aromatic. If a compound is planar, is cyclic, is conjugated, but does not obey Huckel rule, that compound is not aromatic. So all the 4 rules must be obeyed for a compound to be aromatic. Now let's look at the example of aromatic compound using Huckel rule. If you look at the slide, you see that benzene has his pi electrons. Why? Because each of the double bond is 2 pi electrons. Remember I said for a bond to form, each compound is going to contribute 1 electron. So each bond is made up of 2 electrons, right? 2 pi electrons. Now, benzene has 6 pi electrons. How do I validate it? Using Huckel rule. 2n plus 2. 4n plus 2. My 4, n is 1 times 1 plus 2, making it 6. Meaning that benzene has fulfilled the criteria of aromaticity. I've come to naphthalene. My n in naphthalene is 2. 4 times 2 is 8 plus 2, 10. Naphthalene has 10 pi electrons. So it's fulfilled the rule of aromaticity. I've come to anthracene. Anthracene have my N to the 3. 4 times 3, 12 plus 2, 14. Looking at the electrons, it's fulfill the rule of 4n plus 2 pi electron. They are planar, they are conjugated. Conjugated in the sense that single bond is alternating double bond. That's why they are conjugated. So they are planar because I can see each of the sides from one angle. So meaning that they are cyclic because they're in a ring. They are not aliphatic. So these are the rules that have validated that these compounds, benzene, naphthalene, and anthracene, are aromatic compounds. Any question here? I continue.
Question mark.
Any question?
No, ma.
So, okay, thank you. Let me continue. So this is your work.
No.
Which of the compound is, this compound is aromatic? So let's go. Is one aromatic?
Yes.
One is not aromatic.
No.
Who can answer why is one not aromatic?
No, ma.
It's not conjugated.
It's not.
It's not conjugated.
Who can answer?
It's not conjugated, ma.
It's not conjugated.
Yes, conjugation was interrupted in the first ring, right? The first standing ring, right? Have you noticed it?
Yes, ma. Yes,
Yes.
ma.
So whenever
Yes, ma.
whenever there is two single bond, we call it isolated. So that ring is isolated because of those two single bond before you have double bond. So because of that, it's not aromatic. So let's check number 2.
Yes, number 2 is aromatic.
It's aromatic. It's aromatic.
It's aromatic.
Aromatic. Okay. Number 3. Number 3.
It's not aromatic.
Aromatic.
No, it's not
It's
aromatic. Number 4.
It's not aromatic. Also not aromatic.
Number 4.
Also not aromatic.
Number 4 is not aromatic.
It's aromatic.
So we only have one aromatic compound. So it's only 2 that is aromatic.
Yeah. Yes,
Now,
ma'am.
in exam, if looking at using Huckel rule, just confirm the conjugation first. If all the compounds are conjugated, then we can employ Huckel rule. But as long as one rule is disobeyed, they can never be aromatic, right? So that's a good one. Please, we are following.
I have a question, ma.
Okay.
But how do you determine the N in Huckel's rule?
Who can tell me how we determine N?
The number of rings.
Good.
Number of
It's like
electrons.
she's just joining. It's the number of rings. So somebody is just joining. That's why. That's how we know latecomers. When after burial, people that came late, when they went to a Zoom, they were Zoom from the head. Because they were not when the burial was done. So that will happen to you. So welcome to class. So let's continue. Now, these are something that all aromatic compounds must have in common. Number 1, they must be resistant to oxidation. They must undergo substitution reaction, thermal stability, and they must obey Huckel rule. Now, this is property. It's different from characteristics of aromaticity. So don't bubble the two up. If the question says, what are the character of benzene that confirm that it is aromatic? It's different by saying, what are the characteristics of aromatic compounds? When you're talking about benzene, you talk about benzene is resistant to oxidation. Benzene has unusual thermal stability. Then, when you do this, then benzene is resistant to addition reaction. This is for benzene, this is uniqueness of benzene. when you're talking about what are the character of aromatic compounds, you're not talking about benzene, you're talking about general. Then that's what you're talking about, being cyclic, being planar, being conjugated, and obeying Huckel's rule. Then when you're talking about properties of all aromatic compounds, remember, the first one is benzene. Second one is, the first one can be called properties of benzene that confirm that it's aromatic. Second one, general characters of aromatic compound. This one is the properties of all aromatic compounds. The properties of all aromatic compounds is like combination of the properties of and characteristics, because you are picking up the Huckel's rule as the characteristics. Others are what you can talk about from properties of benzene that confirm that benzene is aromatic. So it's a combination of the two. So why I'm saying that the answer to question is dependent on the nature of question. So what affects students so much in this 213 is the question that is asked. Don't go and memorize. When you cram chemistry, you'll be destabilized. Understand it. That's why I'm taking my time to also, when I come to a place that might be confusing, I have to explain it for you to understand. So you don't move both things up together, especially because this course is CBT. So if you're not careful to read in between the lines, you might see two similar options. So whenever you enter exam hall and you're reading options, please read to the end. If you feel like you've read it before, you've revised it before, you know. Don't ever be in rush to make an option, because as soon as you click, that's your decision. Your examiner don't want to know whether you made a mistake, you didn't read it to the end. That was your own cup of milk. So you must make sure that whatever you're doing, that you read to the end. Is that okay?
Yes, ma'am.
Yes, ma'am.
Okay, so let's continue. Now, the next slide now. Nomenclature of benzene. How do we name compounds that involve benzene? Now, if you're talking about a derivative, it means that in the derivative, one of the hydrogen of benzene has been replaced with an electrophile. Remember, the reaction of benzene is electrophilic aromatic substitution reaction. So this hydrogen replaces with another electrophile. We call it derivative. Derivative means derivative of benzene. Either you look like your father. I'm sorry, the network logged me out. I'm sorry. Out. Sorry, I was locked out. That doesn't mean that we should start making noise again. Okay, like I said, derivative means I obtain from. Please, let's put ourselves through. Now, in derivative, just like when you have twins, it means you've replaced two. Then when you have one, so we can talk about twins to be di-substituted, while one is mono-substituted. So we have mono-substituted derivative, while only one hydrogen is being replaced. And we also have di-substituted when two hydrogen is being replaced. Then benzene minus one hydrogen becomes an alkyl called phenyl. Phenyl is like methyl. When methane loses one hydrogen, it becomes methyl. Or when any document. When any alkane.
One class is 12 to 2, another one is 1 to 3.
What's the noise for?
So now that I don't MJ. I mean, I don't join the people now.
Hello, somebody is disturbing my class. Everybody should mute themselves. Everybody, oh my goodness, what would I do to these students? David Otunuga, please mute yourselves. Otunuga David, Ilori Ayolua, Dele, Cleopatra, Atanda, please be muting yourselves. So. Oladosu, hey, you guys are good students, so you should not prove otherwise. I believe that you guys are smart. I know how to use your online handle. Please mute yourselves, I beg. So we are talking about nomenclature in benzene. So when benzene loses one hydrogen, call it phenyl, it becomes a substituent. Just like when alkane loses one hydrogen, it becomes alkyl, serving as a substituent. A substituent is what cannot stand on its own. It has to, just like as you are now, you're a substituent. You cannot stand on your own. Except some of you that are making money, that you're taking care of your school fees. But as long as you take your stuff from your parents, you are still a substituent. You're not on your own. So let's get to the next slide. We can also have a di-substituted, like I said, when two hydrogen atoms are being replaced. Now, how do we name? It's easier to say name mono-substituted. It's only when you talk about di that you talk about how we name, because you start considering alphabetical order. So in di-substituted benzene, we have three isomers. We have auto, we have meta, we have para. Auto isomers are 1,2 di-substituted benzene. While meta is 1,3, para is 1,4. Remember, benzene has two sides. Now, looking at this benzene, if you want to name, if you want to number benzene, you can number 1, 2, 3, 4, 5, 6, right? If you number 6, each side, 1, 2, and 1, 6 are equivalent. I want you to draw benzene ring and number it 1 to 6. Draw it on your and number 1 to 6. Done? Are you done?
Yes, ma'am, we are done.
Okay,
Yes,
1, 2, and 1, 6 are the auto position. Position 1, 2, and 1, 6 are auto position. Taking. So meaning that if my substituent is at position 1 and 6 or 1 and 2, they are the same thing. So position 1, 3, and 1, 5. Position 1, 3
What are we waiting for?
and 1,5 are the same.
She came.
They are the meta position.
Hmm?
Why position 1,4 is para? So 1,4 is 1,4 anywhere. Para is only one position.
What are
We
we
have
waiting for?
1 total, we have 2 meta, and we have 1 para. So that's the 3 isomers of disubstituted benzene.
Two substituted. There's two.
Disubstituted benzene have 3 isomers. So let's continue. So let's look at a typical example. This is tri-substituted, right? In that case, we are having we are having 3 hydrogen being replaced with substituents or with electrophile. So in that case, we don't call any autometa para here. We just name them alphabetically, the way you know how to name normal nomenclature. So now, if it's the same substituent, assuming in these 3 positions, I have chlorine in XYZ. So I can call it 1, 2, 3 trichlorobenzene. So if it's the same substituent, I can use tri. But if it's different substituents, I don't use tri. I will name them accordingly. So we're going to see examples as we further. Now look at this example now. In this example, I have all the substituents to be the same. And the substituents are nitrogen, NO2, nitrogen dioxide. Now listen, whenever you want to write a compound or put a substituent, remember, the position of the bond matters. Some of you, but in CBT, you might not need it, but people that are in chemistry should understand. If you understand that the first structure, the way that the nitrogen at position number 6 was written, the nitrogen is connecting the carbon bonding from benzene itself. So don't say because it's at the terminal, I just write any O2 anyhow. And if the bond is connecting to oxygen, you're writing different things entirely in chemistry. So make sure that you know that it is carbon that is connecting to nitrogen, not oxygen, because of the valency. So whenever you're drawing structures, make sure you maintain the valency of the atoms you're dealing with. Now, because I'm having the same substituents, so that's why I'm having. Now, my question is this: structure 1 and 2, what is different between them?
The positions of the nitrogen.
From what we said, in essence, 146 and 124, are they not supposed to be the same?
Yes, ma'am.
Those first structure and second are supposed to be the same. They're supposed to be 124. They're not supposed to be 146. Why? Who can answer the question?
Why naming organic compound?
Yes.
We use the list number, the addition of the first number.
Good.
1 plus 4 plus 6 will give us 11. So 1 plus 2 plus 4 will give us 7.
Another reason, I want another reason, like what we explained before. Another reason. Remember that there are 2 different structures. Is when I have the same structure, I will talk about the route to follow. But these one are 2 different structures. I'm saying that 146 and 124 are the same structure. They're supposed to be the same structure in naming. I said why?
Because the NO2 in one side, one has auto and para, and the other side too, it's also in position of auto and para.
I think it's because they are mirror isomers.
You don't answer my question.
Ma'am, because they are auto. Auto as
They are
one
both
side.
auto. 1, 2,
auto
and
and
1, 6
para.
are the same. Yes. 1, 2, and 1, 6 are the same position. So if I have position 1, 2, and I have position 1, 6, I cannot call it 1, 6. I'll still call it 1, 2. In that essence, I'm going to start naming anti-clockwise. I'll start numbering anti-clockwise on the first structure because they are the same auto position. 1, 2, and 1, 6 are the same auto position. So I cannot name it 1, 6. Instead, I will follow my anti-clockwise when numbering. So whenever you want to number, you follow the routes that will give the minimum number. So I cannot name 1, 4, 6. I will name it 1, 2, 4. So let's continue. Now, like I said, the substituent that is added to this benzene is going to define the functionality of the benzene compound. We are entering into another section of benzene. So the substituent matters. Remember, phenyl is when benzene loses 1 hydrogen. So the attachment added to this phenyl will determine the functionality of this benzene family. Remember, we are talking about derivatives of benzene compound. So look at the functionality now. If I'm adding alkyl, if that hydrogen is being replaced with alkyl, we are going to form alkyl benzene, also called arenes. If they are replaced with halogen, we call it aryl halide or halobenzene. Now, the substituent will define the family of this benzene. If it's amino group, we will call it aniline. If it's hydroxy, we call it phenol. We have aromatic benzaldehyde if it's aldehyde functional group. We have aromatic ketone if it's ketone functional group. We have benzoic acid if it's benzoic functional group. And we have nitrobenzene if it's nitro substituent that is being replaced by that hydrogen. So the substituent determines the functionality of the derivative of benzene. So you should be able to know that whenever I'm seeing alkyl in benzene, it changes to be benzene. We are going to see a typical example as we proceed. Now, how do we obtain this benzene and other aromatic compound? Their major sources are coal and petroleum. And the process is via distillation. When you do carbonization of coal, which is called destructive distillation of coal, we're going to yield benzene. So distillation of coal tar will also yield some major fractions of aromatic compounds such as phenol, anthracene, phenanthrene. That's why these are hydrocarbons. And hydrocarbon, that's why I want to also bring out a point whenever you're eating your suya, you're taking hydrocarbons. That's why they're very poisonous to you. You guys are like a fizzy. You like to go to those places that are doing chicken and chips. They are roasting turkey and chicken. All the smoke there, they are hydrocarbon byproducts. And whenever you're eating them every day, you're killing your kidney. That's why there is high rate of kidney problem. Every time you're consuming it, you're doing shakara, feeling you're living life. They know you're killing your system. So as much as you want to do them occasionally. Let it not be a habit. So you don't kill yourself before your time. Now, we are still on sources. If I see anybody laugh in the class, I'm going to mute you out. I know people that are disturbing my class. By the time I start punishing them now, they will start apologizing. Elosho, Olua. It's like Miriam is tired of muting you people because you're giving her headache. Is Eniola smile here? Is Eniola in the class? Please, attendance is very important. Because when the chiefs are down, I will know some of you will come and start begging. Now that it's time for you to do the right thing, you will not come to class now. The class is online. But for you to come to class is difficult. When the time comes, start begging. Start writing letter. Elosho, Olua, this your name is speaking in tongues. I asked a question, you're raising your hand.
If Fenil in our queue can expand alone, if it's a compound.
I can hear your voice is faint.
Oh, I said I wanted to ask if Fenil in our queue can stand alone. I can hear me.
I can still understand you. Can you increase your mic?
Hear me now. Now can you hear me now?
Okay, better. I can hear you.
I wanted to ask if Fenil or alkyl can like stand alone, since according to the definition, Fenil is benzene with one H removed, and then
Yes.
it was part of the benzene derivative. So I wanted to ask if it's a compound.
No, it's not a benzene derivative. It's a substituent. That's why it's not balanced, and that's why something needs to come and balance it. Right? That's why we're having those substituents added to it to make it balanced. It cannot stand on its own. Just like you have a seat that one leg removed. The seat is big, but it cannot stand on its own. What you need just one leg to make it stand. Do you understand that?
Yes, ma. Yes, I understand. Thank you, ma.
Yes. Welcome. Any other question? So let's continue.
Ma, I have a question, ma.
Okay, go ahead.
Sorry, did you just say benzene cannot stand alone? Or I don't understand.
Phenyl.
Okay. Thank you.
Phenyl is benzene that loses one hydrogen.
Okay.
Yeah. Any other question?
Ma, I have a question, ma.
Okay, which question again?
Ma, for this compound, for this unsaturated compound, like benzene to take place, like for reaction to take place in this compound, the p orbitals in the compound, or like like their position are, like, for example, now, if a particular compound with p orbital want to react with another compound with p orbital, like the position of the p orbital, are they to be perpendicular, or how are they to be placed to one another for a reaction to take place?
See, a reaction of that has to do with benzene. The p orbital is not reacted because they are in a ring. They are cyclic. They are covered, so they are not exposed for reaction. Remember, any reaction that is occurring in aromatic compound, they are occurring by substitution, not addition. So the ring is not affected. So the p orbital is not visible here. You only talk about p orbital when you're talking about your aliphatic ring, when they can react. Okay, but here, now talking about perpendicular is that the p orbital lie perpendicular to form the double bond.
Okay, ma.
Yeah.
Thank you, ma.
Welcome. No more questions, so we can continue. Now, we're talking about, now, petroleum is another source of benzene and aromatic hydrocarbon. Remember, we'll talk about coal, now we'll talk about petroleum, we'll talk about coal and petroleum. So, in terms of coal, we'll talk about carbonization of coal. We'll also talk about destructive distillation of coal. This carbonization is also known as destructive distillation of coal. And we'll talk about distillation of coal tar. Then, in terms of petroleum, we're going to use catalytic reforming to form all these benzene and their derivatives. Oh, noisemakers. Somebody should, hello? I think I have to, please, somebody should be, Miriam, what you should be doing for me is that anybody that mutes themselves and they're making noise, just write the person's name and matric number. Don't bother telling them to mute again. I know how to handle them. Just write their names. Anybody, whenever I come online and I see people that unmute themselves, I'm going to write out their name. I'm going to penalize them. My own method of penalizing, you will not know it. John, and Cleopatra. People have been disturbing me since today. Please, Miriam, write all the name of people that unmute themselves. I don't know why you take pleasure in unmuting yourself. Please help me note their names. And I'm going to use another person that will be another a co-host that will be the course rep in this class. You guys are just disturbing my class. Who is Achebe Chidera? Achebe Chidera, are you around?
Yes, ma'am.
Okay. Achebe Chidera, I'm going to make you a co-host. What department are you?
I'm cell biology and genetics, ma'am.
Okay, so I'm making you a co-host. You and okay, Miriam is not my co-host. So. Miriam, where are you? Is Miriam in the class? Miriam is not in the class. Chidera, can you help me monitor this class? Miriam, are you in the class?
Yes, ma'am.
Okay. So I'm going to make you a co-host again. I'm looking for you. Okay, Miriam. You're Okohoro. Are you? Are you Marion or Miriam?
Marion.
Okay, fine. Please, you guys should monitor the class. Anybody that unmute themselves, you write their names out.
Okay, ma'am.
As you're writing their name, you're muting them. Write their names or their matric number, any identity of them.
Okay,
because
ma'am.
I'm going to penalize them that disturbing my class. By the time I remove their name of people that will join the class, they will understand. So when you talk about coal, you talk about petroleum. You can talk about destructive distillation, and you also talk about catalytic reforming for petroleum. What are the properties of benzene? Benzene is a colorless liquid. Now, remember, liquid boils. So for it to boil at 80 degrees, it means it's a liquid, and it melts at 4.5 degrees. It means is that it's a liquid that is not very light. That's why it can melt. It has a characteristic aromatic odor. The odor of benzene is not very pleasant. Now, benzene does not mix with water, meaning because it is what? Non-polar. It is oily. That's why it cannot mix with water. And the density is lower than water, meaning it can float. When we are doing 223, we are talking about how to know aromatic compound using smoky flame. Benzene is going to burn with smoky or sooty flame, which is due to their unsaturated nature. In 223, we call it sooty flame. It's also known as smoky flame. Smoky flame, and they cannot decolorize because they are aromatic. Other unsaturated can decolorize, and they can also form smoky or sooty flame. Who is talking now? Anybody that talk? Zainab. Write Zainab's name. Zainab is disturbing my class. Anybody I tell you to write their name, just be writing their names. So any compound that burns with sooty flame or smoky flame using a flame test is a typical unsaturated compound, whether aliphatic or aromatic. Whether aliphatic or aromatic. The reactions of benzene. Remember, I said that benzene undergo a typical reaction called electrophilic aromatic substitution reaction, because the hydrogen in benzene is regarded as electrophile. So this hydrogen is going to be exchanged with any incoming electrophile in reaction. And I also said that benzene cannot undergo addition reaction because it must protect its aromatic nature. And benzene is very stable due to its resonance energy. So typical reaction you must not forget for benzene is, remember I said electrophilic aromatic substitution reaction. If you do not add aromatic in your CBT, you can see options like electrophilic substitution reaction. You can also see electrophilic addition reaction. You can also Oluwaseun, I don't catch you. You can also see electrophilic addition reaction. Then you can see electrophilic aromatic substitution reaction. People that are always in a haste, immediately they see electrophilic and they say substitution, they will not see there is no aromatic, they will pick it. In every option, there are two that are very similar, but one is more correct than the other. So that's why you have to take your time and don't be in a haste when you're answering CBT. Now, because of the stability of this benzene, when it wants to react with compound like halogen, conditions like heat or catalyst are being involved. So it's under severe conditions that benzene can undergo hydrogenation reaction. So whenever you're writing any reaction that has to do with hydrogenation for benzene, whether chlorination or bromination or iodination, any reactions of benzene you want to write, you must include the catalyst. And the catalyst for benzene has to do with what you're doing in halogenation. Remember, benzene cannot react with permanganate, whether cold or hot, because of oxidation. And benzene does not react with bromine in tetrachloride, because these are typical oxidation reaction. Decolorization of bromine water and stuff. It cannot. Whenever benzene wants to react with bromine, it will use a catalyst, ion catalyst. Now, if it's bromination, you're going to use ion trichloride. If it's chlorination, you use ion trichloride. If it's bromination, you use ion tribromide. So it must be ion catalyst that you're going to use, and depends on the halogenation reaction that is occurring. So I cannot be brominating and I use FeCl3. And I cannot use FeCl2. I cannot even use FeBr2. It's ion 3 catalyst of the halogen that is undergoing the reaction. Some of you will go and write, you want to brominate Br2. You come and write FeBr2. Please note all this. These are small questions, small mistake people make. Because even in the OBJ, you're going to see FeBr2. You're going to see FeBr4. So you're going to see things that are very, very similar. So that's why whenever you're reading OBJ, you don't just rush it as you're reading up. You have to study it to know the differences. Reading between the lines. And you cannot be brominating and use FeCl3. I hope this is taken and noted. So these are the typical reactions of benzene we're going to be looking at. We're going to be talking about electrophilic aromatic substitution under nitration. We're going to talk under sulfonation, under halogenation, under Friedel-Crafts reactions. Friedel-Crafts have two reactions, which are alkylation and acylation. So we're going to look at this when we are talking about reactions of benzene. Any questions so far before we proceed? Ask your question. Please, attendance is important. If there's no question, no question, right? Lambukimi and Ogunyika. Please write their names in noisemakers. Write their names, Ogunyika and Lambukimi. Write their names. Boluwatife, write their names. They are disturbing my class. Oluwatobi Loba. Okay, let's continue. Now, I have to take it easy here on this mechanism because it's very, very important. It's important for you to understand why we are talking about the localization of electron cloud in benzene. So now, this is general mechanism from electrophilic aromatic substitution reaction. This is benzene with conjugated bonds. In the presence of an electrophile, this electrophile, remember what electrophile does? Electrophile normally attack to remove one hydrogen. So in the mechanism, this electrophile is going to break the bond to fix itself. So in that case, you can see that we have an electrophile and hydrogen. Then, this is what they call slow stage. I would have loved this to be done in the class, but since you are doing online, we'll try to optimize it. Now, the second slide. Whenever there's an attack, when this electrophile attaches itself, because a bond is broken, remember a bond is made up of positive and negative sides. An electrophile is positive already. So electrophile is going to come and bond in the negative section of this bond and generate positive. That is why you're seeing positive there. Then my arrow is going to move towards that positive to neutralize the positive and create positive, right? Because when a bond is where a bond is moving to, is going to deposit negative center. And where the bond is moving away from is going to leave positive species. Because whenever you're giving, it is to the person, base. That is why it's negative. But to you, it is positive. That's what happened. When you go to withdraw from bank you're collecting, and bank said it is negative debit. And when you go to give, they said it's positive, that is credit. So whenever this arrow is moving to, the arrow is depositing negative center. And this negative center is going to neutralize the existing positive center to form a bond. Like I said, a bond is made up of positive and negative centers too. So whenever they are breaking, that's whenever you're talking about, I know that the first lecturer taught you about heterogeneous reactions or species, where you have positive and negative center. Now, when this bond moves, remember we have a positive species generated by an electrophile that entered. Then this arrow is going to move towards that positive center to neutralize and form another positive. So in that case, I'll be moving anti-clockwise direction because my positive center is in clockwise direction. I'll continue to move until the last structure when I have I, why there is a species, a positive species there. Now, the last IV is a hybrid, telling us that this positive center moves across all the sides of the ring. Remember, if you look at the two auto position and one para position, that's where we have positive species. So that's why that dotted resonance hybrid structure is representing that this positive center are on the two sides of the auto and the para. So that's the last structure, which is IV. IV is a resonance hybrid of all the 3 steps. Step 1, step 2, step 3. If you look at step 1, step 2, step 3, you talk about auto and para. So this electrophile is auto-para directing. We are going to talk about it when we get there. You'll understand what I mean. Just here, auto-para directing. In exam hall, you might not be expected to, nobody will expect you because you're doing CBT for you to start drawing the canonical structure or the mechanism of electrophilic aromatic substitution reaction in benzene. But for you to understand now, at the end of the reaction, we are still going to have, which is what happens here, we're still going to have the bond formed. Now, if you look at where the bond started, you can see there is a movement, there's a shift. The bond has taken another shift entirely because as they are moving, they're going to change position. There's going to be a shift. This is what we have here. So everything that happened in the last slide is what happened in the slow stage. Then in the fast stage is where the reaction is occurring. Everybody will be all right. Everybody will be all right. Now, at the last end, this nucleophile is going to come and take hydrogen and the bond will form back. So let me go back to it again. In this mechanism is telling us the step for the reaction to occur. Just like somebody saying, I'm coming from Sango to Unilag. So the reaction is Sango transport Unilag. That's the reaction. But mechanism is from Sango, I entered bike. I got to this place. I light. I entered a keke. So these are the steps it took before getting to Unilag. So that's what is happening. But the simple reaction is that from Sango to Unilag. But it does not happen that way. There's so many steps in between before getting to Unilag. So in this mechanism, we are talking about how is it that this benzene is going to undergo this electrophilic reaction, and this hydrogen is just, it will just be removed and the electrophile will be added. How does it happen? So that is the process we are undergoing. By saying that when this electrophile come into the ring, because it's what it's coming to do is to remove hydrogen. It cannot just remove hydrogen. It will just look a means of attaching itself. When it attaches itself, it's going to produce a positive species. So now I am moving to neutralize the positive because I want to change the bond. Remember, with Kekule, August Kekule said the benzene ring is a hybrid of 2 canonical structures. So that is what happens. So at the end, the ring I started with, look at the ring we started with. If you get to the end, you realize that there's change of bonding in the product we are going to end with. That is mechanism. So as soon as the positive center is being generated, the arrow will move in that direction to neutralize the positive center. And as it's neutralizing, it's creating another one. At the end of the reaction, that hydrogen that is being bonded is going to come back, an electrophile, a nucleophile, which is the negative center. Remember, this hydrogen is an electrophile. And what is going to take it out is a nucleophile. So a nucleophile is going to come and take this hydrogen so that the electrophile will stand without having anybody disturbing it. And thereby, the bond that was broken then regenerated. That is what happened in all this process. But as long as 213 is concerned and your CBT is concerned, just understand this. Understand that we have canonical forms in the mechanism. Canonical forms are the points we have positive centers. They are the canonical forms. Then the resonance form is the one that is telling us that at the position 2, at position 6, at position 4, we have positive centers. So that's why it's represented with dotted lines and positive at the center. So we'll call it a resonance hybrid. Why structure 1, 2, and 3 are canonical structures. When you get back, because I've shared this slide with you, go through the slide and see if this mechanism makes sense to you. And if it doesn't, we'll talk about it. Now, I don't want you to be confused. This other hydrogen, see that hydrogen that is where there is positive center. Whenever you're writing your notes, remove that hydrogen. That hydrogen is not meant to be there. It's not meant to be announced at all. The only hydrogen that is supposed to be seen is that hydrogen that is bonding with electrophile. And that's why I see the other ones, or the other subsequent rings, that other hydrogen that is attached is not there. It's not supposed to be there. So as soon as that electrophile bonds, the hydrogen is going to be attaching itself with it, because that's why there is no bond in between them. Because that bond there, they've shared it. And we have a positive center because the electrophile is going to come and bond with negative section of that bond. There is a bond that is where this hydrogen is. That bond was broken. And that negative center is where the electrophile came and attached. And we have positive center remaining. Then because I have positive center, I have to move in a manner to neutralize that positive. That's how I have to, my arrow is going to move towards a positive center. The arrow is depositing negative on the carbon. Remember, we are dealing with carbon. Deposit negative on the carbon. Behind it is going to leave another positive on the carbon next to it. So because there is negative on that carbon and the upper carbon has positive, a new bond is formed there. And behind is a positive center. So the arrow will move again in that manner to deposit negative in a carbon next to the one that have positive center to form another bond. That's what we have in carbon in the structure III. Having positive left at another auto position 2. Now, when this hydrogen breaks off, it's going to break off by the bond breaking in. When the bond breaks in, it's going to release negative center beside this electrophile point. So that is why a new bond will form there, because there's already positive that's waiting. So when the hydrogen is going to be going, it's going to deposit negative center to form another bond to close the ring. And that is what we have here. And the ring is closed. Then look at this final ring that we have here, where electrophile is standing on its own without hydrogen. And with the one we started, is there any change in position of double bond? Look at it very well. Look at what we started with. Look at where the double bond is. And look at what we ended. Look at where the double bond is. Is there any change in position of the double bond? Somebody should answer me. Is there any change in position of the double bond?
Yes,
Yes. So that's what we're talking about, the localization of bond. So the bond have delocalized from where it was, and it has changed. Now, if you look at it, you understand why Kekule said that these bonds are not stable. They are delocalizable. And that's why Kekule represented the bond of hexane, the structure of hexane, to be canonical structure of two hybrid. So that is what we have here. So just understand that we have two canonical structures and also one resonance hybrid. And that resonance hybrid is represented with dotted, with plus, meaning that in position 2, 6, and 4, there are positive centers. So that is what happened in the mechanism of, general mechanism of electrophilic reactions of benzene. So I don't want to go further because our time is almost up. So I want to take your questions so that we can start on this slide, the next class, which is on Thursday. So ask your questions. Anything you don't understand that you want us to throw more light on.
Ma, I have a question.
Go ahead.
Emma, that first reaction between benzene and that positive ion, Which among the two is an electrophile?
Are you talking about this?
Yes, ma.
The electrophile is now electrophile. Now, if you're doing bromination, right? Bromine
Okay.
becomes an electrophile.
Okay, ma.
If you're doing nitration, NO2 becomes electrophile. So E is representing electrophile. Like I
Okay.
said, that hydrogen that is connecting this positive center is supposed to be expunged. So whenever you're drawing your structure, remove that hydrogen. They will only have one hydrogen that connects with the electrophile.
Okay, ma.
Yeah. So any other question?
Ma, I have a question again.
Okay, go ahead.
That structure I, which gave us the resulting structure IV. Can we also call that the resonance structure?
They are resonance structures.
Okay,
The other
ma.
one is resonance hybrid.
Okay, ma.
Yeah.
Ma, and my third question is that fourth structure formed, is it an aromatic compound?
All the compounds are aromatic.
Oh, ma, but that if we check III structure III, I don't think it's obeying conjugation.
No, because we are doing this is mechanism. They are undergoing. They are on a process. They are not a complete compound. You can't see they have positive species everywhere.
Okay.
So you can they are not compound, but they are aromatic. So it's at
Okay.
the end you confirm whether they're aromatic or not. But whenever
Okay.
you are having a electrophilic, nucleophilic, you cannot talk about aromatic or non-aromatic.
Okay, ma. Thank you,
Yeah.
ma.
Any other question? From any other person? Please ask question.
Sorry, ma. Which
Because
one is
that'll be a
nucleophile?
class work. Okay. What's the question?
Which one is the nucleophile?
A nucleophile is a negative center. A nucleophile is anything. Now, we are going to be seeing a typical example in the next class. Okay, a nucleophile is a negative species. They attract positive centers. They're electron loving. They are negative centers, so they need a positive species to neutralize themselves. Right?
Okay, ma.
Now,
Thank
if
you.
you look at this, if you look at this last aromatization, you realize that a nucleophile is a negative center that is going to attract an electrophile. Now, in chemistry, unlike attracts, right? Now, for an electrophilic substitution reaction, it means that this benzene, the hydrogen that is going to leave what? What center is this going to leave for? Electrophile to come and attack from the mechanism that we just did now. At what point is electrophile attacking? Is it attacking at the positive center or the negative center?
The negative center.
Yes, because it is a positive species already. So a nucleophile is a negative center that need a positive species. So the hydrogen coming out now is a positive species. So that nucleophile is a negative species that is going to neutralize, form a bond. Do you understand?
Yes, ma. Thank you, ma.
Yeah. So hydrogen is going to be lost as a proton, which is a positive species. And a nucleophile is going to take it, accept it. So a negative species is looking for a positive center. A positive species is looking for a negative center. Any question? Any further question? Can we take our classwork now? Your pen and paper. Question number 1. Are you ready? Are you ready for your questions?
Yes, ma'am.
Question 1. Why is it that benzene does not undergo usual addition reaction of unsaturated compound? At the end, I'm going to create a Google Classroom where you're going to submit your classwork. But I want my co-hosts to note the classwork so they can paste it on the platform. Why does benzene not undergo addition reaction? Question number 1. Why does benzene not undergo addition reaction? Question number 1. Taking. Why does benzene not undergo addition reaction? Question number 2. Nobody should disturb me. Question number 2. Anybody that does not attend the class will not submit. Let them know. Question number 2. What is a typical reaction of benzene? What is a typical reaction typical of benzene and aromatic compounds?
Garlic. Okay.
Number 3.
No,
Who is disturbing my class? What is the hybridization in benzene? What is the hybridization of carbon in benzene? What's the hybridization of carbon in benzene? Then, under that question, this is A. The B of this question 3 is this. What's the hybridization of carbon-carbon in benzene? What's the hybridization of carbon-carbon bond in benzene? The first one is what's the hybridization of carbon in benzene? Second, what's the hybridization of carbon-carbon bond in benzene? That's the B section of question number 2, Abi, or 3. Then the C section is what's the hybridization of carbon-hydrogen bond in benzene? Hybridization of carbon, hybridization of carbon-carbon bond, hybridization of carbon-hydrogen bond in benzene. Taking?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Thank you. Now, how many 1,2-disubstituted isomer do we have in benzene? How many 1,2-disubstituted isomer in benzene do we have in benzene?
Please come here.
How many 1,2-disubstituted isomer do we have in benzene? In benzene, not benzene derivatives.
3.
What are the characters of benzene that confirm that they are aromatic? What are the characters of benzene that confirm the aromatic behavior? What are the characters of benzene that confirm the aromatic behavior? Next, what are the general characteristics of aromatic compounds? What are the general characteristics of aromatic compounds? What are general characteristics of aromatic compounds? Name the two sources of benzene. How many canonical forms do we have in electrophilic aromatic mechanism of benzene? How many canonical forms? Or how many resonance stabilized intermediates can you form in electrophilic aromatic substitution reaction mechanism of benzene?
Ma, please, can you come again?
How many canonical forms or resonance stabilized forms can you find in benzene? How many isomers are possible in disubstituted benzene? Mention them. How many
Please come
questions so
again,
far?
this question before.
It's not the same.
Ma, you've asked it before.
Ma, please come
It's
again
not the
with this
same.
one.
No, she hasn't asked
Come
it
again.
before. This one is a different one.
That's
Ma,
why
please come
I
again.
was stressing on it. Go back to your slide.
Ma, please repeat the question.
This one, what did I say? How many isomers is possible in disubstituted benzene? Disubstituted benzene. That one is confusing, right? It's looking like the first, but it's not the same. Any question on the question I sent so far? Then the last question. The first question I said, how many isomers do we have in 1,2-disubstituted benzene? 1,2-disubstituted. 1,2-disubstituted. The other one I asked is, how many isomers do we have in disubstituted benzene? Are they the same question?
No, ma.
Okay,
No, ma.
thank you.
It's clear now.
Okay.
No, ma, it's
So
clear.
the last question,
class.
the last question is, what are the hybridization in alkane, alkane, and alkyne? What is the hybridization in alkane, alkane, and alkyne? What's the hybridization of carbon in alkane, alkane, and alkyne? That's the last question. So ask questions if you don't
Hello, ma.
understand it.
Ma.
Okay, ask your question, yes.
Now, like you gave us this classwork, the mode of submission and when should we submit?
And that's what I'm saying. One of you should just write all these questions and share on your page. I've told your course rep to add me in that class, your platform. Hope you have a general platform for Chem 213.
No, we have a general group for our department.
No, please, I want there to be a general platform for chemistry for 213.
Okay,
Yes,
ma.
ma. We have, ma.
Okay, so that we can disseminate information as regarding the course. Okay, so I'm going to create a Google Classroom, then I'll share it on that platform. Then where the people, anybody that I know that got the questions very well, will share the question on that platform. So I can use this to create your question on the Google platform. So you go there and submit. And submission deadline should be, I will put the deadline. If you're having the class on Thursday, the deadline should be Wednesday evening before 12 a.m. on Thursday. Before 12 a.m. yeah, on Thursday.
Okay, ma.
Exactly.
Okay, ma.
Please,
Ma,
attendance is compulsory for this
ma,
class.
we are still having your class on Thursday.
Yes.
Oh,
So
okay.
you have to submit before that class. So
You would have sent
12
the Google
a.m.
form. You will have sent the Google form.
I will send the Google form today.
Okay.
Just make sure you create it. Who will have help us to create the platform?
Ma,
Who
we
is
have a
studying now?
platform already. Ma, we have a platform already.
Not general for 2 and 3.
We don't have a platform
Yes,
for session
class
213.
reps.
Yes,
We have
we
a
don't have a
platform.
platform for
Ma, we will inform our class rep.
Class reps Ma, now.
Is it for 2 and 3?
Yes,
Yes,
It's not
ma.
for
inform
213.
our class rep.
Yes,
We don't have for
ma.
213 yet. Are you the only
Yeah,
one in the
We
group?
do have a
hello?
platform. The
Yes.
class reps have a
Please.
platform already, and they've added the
Hello?
lecturer to it.
It's not for
Please.
213.
Platform for
It's
2
talking about
and 3.
everybody.
For 2 and 3.
The
For
class
Ma, we
2
don't
and
have
they
3.
need
yet. We
information.
don't have
Yes,
yet.
ma, we have.
We
Ma,
don't
we
have
don't
yet,
have
Somebody
yet.
should create the platform for 2 and 3.
About
Okay,
everything.
ma.
everybody that
Who is the
was
course rep that is here?
Ah,
Marion. Marion. I want Marion and Achebe create a platform 2 and 3, then share it on the general platform. I want it to be exclusively for 2 and 3, not for all courses, so that we can disseminate information exclusively for this course.
Okay.
Yes, create it and add me too, and other lecturers, so that we can be sharing information. Please.
Okay,
Okay, ma.
Thank you. Any other question?
Ma, that's if they create the platform now, all students that is doing CHM 213, be it from different departments, will be in that platform.
Yes.
Okay. Okay, ma. So this particular classwork gave to us.
Irrespective of your department, everybody will be on the one platform.
Okay, ma. And ma, this particular classwork you gave us now, if you give us the classwork on Monday, before 12 p.m. on Thursday, we should have submitted it, right?
Before 12 a.m.
12
By
a.m.
11:59 p.m. on Wednesday, you should have submitted.
Okay.
11:59 p.m. on Wednesday.
Okay, ma. So if it's on Thursday, so 11:59 p.m. on Sunday, we should have submitted.
Yes.
Okay, ma. Okay.
Attendance is compulsory.
Ma, how are you taking the mode of attendance?
Yes. See, anybody at the end, I want to know the course rep from each class. The course rep from each class must indicate. So they will be taking attendance for their classes. Because when the chips are down, the attendance will play it through. So don't think you will just not come to class and tomorrow you come and make complaint. Somebody will listen to you. Please, and I would have loved the attendance to be snapped, a snapshot, a shot of the attendance.
Okay.
So that somebody will not come and do magu for me.
Okay, ma. We'll inform our course.
All right, thank you.
Please, ma, how is the submission going to be? Is it going to be in form of PDF?
Is it your classwork?
Yes, ma.
If MS Word is if you can upload MS Word, good. If it's PDF, good. If your writing is legible and you can snap and upload anything that is readable, that can be accessible. So when you upload, try and see if you can view what you uploaded. If it's viewable, you go ahead. If it's not viewable, you know it's not good. You have to change it.
Okay, ma.
Any other question?
Ma, please, what's your
Can we get the recording of the class?
Yes.
Ma, please, what's your
And the PDF and the slide.
The slide, okay.
Ma, please,
I've
what's
shared
your
the slide already with you. I think I shared the slide. So that's why if you can create the platform, information can easily be disseminated.
ma, what's your YouTube?
So
Thank you.
I cannot be dealing with only chemistry course rep. But whatever you want to
Ma,
listen to, you can go to my Dr. Anita Ken YouTube channel. This topic is featured in audio recording.
madam, if you let us
Anita
know.
what? Anita what, ma?
Kem, Dr. Dr. Anita Anita Kem CHEM.
Oh, thank you.
All right.
Thank you, ma.
All right. So any other question, let me know. If that platform is created, it will be another platform of you asking questions. So I want to encourage you to go and look for past questions. And if you don't have, and anybody's around school, they should come to my office. I'll give you past questions. So I want you to start practicing on the past questions. Don't wait for exam to be 2 weeks for you to start reading. Start reading now, so that you get
Ma,
acquainted with
please,
the way
where?
questions are asked.
Sorry, ma, please, where is your office?
Wait, diploma building.
Okay, ma.
Whenever you want to come, let me know
Thank
that you're
you, ma.
coming, so that I will know whether
Oh,
I'm around. But I'm
all
always
right, ma.
around
Thank you, ma.
Monday, Wednesdays, and maybe Thursdays.
Okay, ma. Thank you, ma.
All right, thank you, everyone.
Ma, please,
So, do you see?
excuse
Okay,
me, ma.
all right.
Thank you very much, ma'am. Bye bye, ma'am.
Can we come to your office
Okay.
now?
Thank you very much, ma. We appreciate ma.
Bye, ma.
Oh, thank you. If you're around, you can come.
Okay, ma.
Thank you. Please, that platform is important, okay? See you in the next class. Bye for now.
Bye, ma.